All right, we got our algebraic equation from the transformed circuit. Now, it will be nice to check if our equation is correct before we move on and massage that equation furthermore. So, how do we actually check if our equation is correct? We're going to use two theorems, the initial value theorem and the final value theorem. And the initial value theorem applies if your f of x is a proper rational function. What does it mean to be proper rational function? It means that if you have your function, and if I rewrite that function as a numerator and denominator, so reduce everything to the same denominator, and if I find the degree of the numerator it's less than the degree of the denominator, then this is a rational function and I can apply the initial value theorem. So if you look closely at this equation, if I reduce to the same denominator, you will see that you have a degree of 2 on the top and a degree of 3 on the bottom. That means that this is a rational function. We are in good shape to apply the initial value theorem. So the initial value theorem is going to give you the initial value for that function. In this case, it's going to give you the initial current. So f of 0 can be found by applying the limit in time when t goes to 0 of your f of t, which we kind of did. And now we are going to do, we did this before in other videos, in the video before this one, and when we were finding the initial current for our inductor. But now we're going to apply the limit of my s when it goes to infinite of an s times your function. Or another way of doing this, sometimes this s going to infinite gives you, it's hard to solve that limit, so we substitute your s by 1 over s and we go and now find that limit when that tends to 0. So let's see an example. We have our current in the Laplace domain, and I'm going to apply the limit when s tends to infinite. The problem with the infinite portion of it is that the second of the equation becomes hard to find a value. So if I substitute by 1 over s and then I get a 0, I can solve that limit. Alright, so if I multiply s by this first function, s's they cancel out, I get 2 plus, and now I have the s multiplied by this one, and if I divide everything by s squared, I'm going to have everything in this form, and I get a 0. So 2 plus 0 gives me 2 amps. Alright, so the initial value theorem, it's actually in agreement with our initial conditions when we found them in the previous video. That means that our equation is good so far. We're not done yet. We still need to do the final value theorem, which applies if all the poles of your s times fs are in the left half of the s plane. So a lot of stuff, a lot of information in this statement. So what are poles and what is this s plane? Alright, so remember that our function in the s domain is a polynomial function, and we have a polynomial on the numerator and a polynomial on the denominator. And on this s plane, on the Laplace domain, if I find the roots of that numerator, I'm going to call that zeros. And if I find the roots of the denominator, I'm going to call that poles. So what is this s plane? So the s plane is just a way to represent visually those poles and zeros. So normally poles are represented with x's and zeros are represented with circles, and you can place them around these two axes, where the x is a real axis and the y it's the imaginary axis. And anything that falls into the left side of your imaginary axis is going to be what's called a stable system. And if all the poles fall into this left side of the imaginary axis is a stable system. If these poles are actually on the right side, then we have an unstable system. The final value theorem is saying that all the poles should be on the left side of your imaginary axis. So let's find the poles of our transfer function. we have this function here, I reduced to the same denominator, and now I'm going to find the roots of my denominator, which are the poles. And if I do that, notice that for this first one, s is equal to 0, so that's pole number 1. And here I have a quadratic equation. If I find the roots of this quadratic equation, I get two poles, they are actually imaginary poles, -1 plus or minus 2i. I go back to the S-plane and I draw those poles into my S-plane. And as you can see here, all the poles are on the left side, so I'm in good shape to apply the final value theorem. In the final value, it's similar to what we did before, where we're trying to find the final current when t goes to infinite. So it's the same thing as going to the time domain and wait a little bit of time and check that value. But in the domain, the Laplace domain, what we're doing is the limit when s tends to 0 of s times f of s. Alright, so we have our equation here. We're going to find the limit when s tends to 0, s times your il of s. If I do that, you see that the s cancels out here and I get 2 plus 0 and I get 2 amps. If I go to the time domain and I find the final condition for my current, you will see that the capacitor is going to be an open circuit, the inductor is going to be a short circuit. So we have a similar circuit as we had for our initial condition. So the final condition, the final current is 2 amps, which is in agreement with the final value theorem.